Welcome back. Now I'm going to do a demo on coiling the Tesla coil. I'm going to describe and read about a little bit about the Tesla coil, the functioning of the Tesla coil, the purpose of the Tesla coil. It's a very famous tool, and this gives you a little bit a diagram of what it is. And then I have a Tesla coil here that I'm going to illustrate, and also another kind of Tesla coil that we're going to show. Okay, and then you'll see the good demo from this. So let's read up a little bit on the Tesla coil. As you know, the Tesla coil was invented by the famous scientist Nikola Tesla. In Wikipedia, this is how it's described. The Tesla coil is an electrical resonant transformer circuit designed by inventor Nikola Tesla in 1891. So this goes way back to 1891. It is used to produce high voltage. So that's the idea. One of the things is high voltage, low current, high frequency alternating current electricity, right? So it's going to be high voltage, and low current, right? So we can say low current. So the high voltage will be produced in the secondary inductance right here, the secondary inductor L2, right? Because we're going to step up the voltage from L1 to L2, and we're going to produce a very, very high voltage. But by increasing the voltage, by stepping up the voltage, you reduce the current, okay? So that's going to be the high voltage, low current, and also high frequency. High frequency. The incoming frequency is from the line that we use, which is probably about 50 or 60 hertz. 50 to 60 hertz, but we increase that frequency to the range of radio frequencies, right? So then it says, Tesla experimented with a number of different configurations consisting of 2 or sometimes 3 coupled resonant electrical circuits. So in this picture that I have 2 coupled circuits, L1 and L2. They're coupled together, but it says Nikola Tesla experimented with 2 or 3 coupled circuits. So it says Tesla used these circuits to conduct innovative experiments in electrical lighting, phosphorescence, right? So you can use a Tesla coil to actually light up a phosphorescent light bulb, X-ray generation, high frequency alternating current phenomena, right? So this is, since it's a high frequency, so he experimented with high frequency alternating current phenomena. Also electrotherapy, right? Electrotherapy and the transmission of electrical energy without wires. So this one was thought to be a way to transmit electrical energy without actually wiring, because this is going to get so high voltage that it's going to produce sparks in the air, right? And it can transmit that electrical field through the air, and other things can light up that are in the vicinity of that object, right? So Tesla coil circuits were used commercially in spark gap radio transmitters for wireless telegraphy until the 1920s. And in medical equipment such as electrotherapy and violet ray devices. Today their main use is for entertainment and educational displays, although small coils are still used today as leak detectors for high vacuum systems. Tesla's original circuits, as well as most modern coils, use a simple spark gap to excite oscillations. So you see, this is the spark gap right here. We call it SG, spark gap. In the spark gap, we tune it so that it can resonate with the LC circuit. You see, it becomes an inductor and a capacitor, right? So it says here, Tesla's original circuits, as well as most modern coils, use a simple spark gap. Most sophisticated designs use transistors or thyristors switches or vacuum tube electronic oscillators. Tesla coils can produce output voltages from 50 kilovolts to several million volts. So imagine here, the output voltage is going to be 50 kilovolts. That's a lot. Basically, you're stepping up all the way from the regular voltage, which is 120 or 220. You're stepping up all the way to 50 kilovolts, 50,000 volts. But it says it can go to several million volts, to all the way to several million volts. Okay. Now it says alternating current output is in the low radio frequency range, so 50 kilohertz to 1 megahertz. So the output frequency, 50 kilohertz, all the way to 1 megahertz. Well, the incoming frequency of the alternating current is 50 to 60 hertz. So we're still stepping up the frequency, right? Very high frequency. 50 kilohertz to 1 megahertz, that's kind of in the range of the AM stations, right? So AM station, let's say the AM station 710, that's kilohertz. That would be AM station, and that's ESPN, right? Sports station, 710 kilohertz. That's kind of in this range, right? 50 kilohertz to 1 megahertz would be 1,000 kilohertz, right? To 1,000 kilohertz. So 710 kilohertz is in that range. So basically we're stepping it up to radio frequencies similar to AM station, right? A high voltage supply transformer to step the AC main voltage up to a high enough voltage to jump the spark gap. So this is the transformer right here. So it steps up the voltage right here. It says to step up the AC main voltage. So from here to here, we're already stepping up the voltage, right? And then there's a when we step up the voltage enough, there's a spark gap that flies from here to here, and it forms a circuit, a current. When that has the same frequency of this, we resonate with it, right? So it says a high supply transformer to step the AC main voltage up to a high enough voltage to jump the spark gap. Typical voltages are between 5 and 30 kilovolts. So that means from here to here, we've already stepped up to 5 to 30 kilovolts. So all the way from 120 volts, right? We've stepped it up from here to, so this one must have more turns, right? Like this. When this one has more turns than that, we step up the voltage, right? From 120 to 5 to 30 kilovolts. But that's not enough. From there, we're going to step up, from here to here, we're going to step up 50 kilovolts to several million volts. So there's a two-step up processes that is happening in a Tesla coil. One from the regular to 5 kilovolts or 30, and then from there to 50 and or several million. Depends how many turns this one has. If it has a lot of turns, then we can step it up to several million volts, right? So the next thing it has to have is a capacitor C1 that forms a tuned circuit with the primary winding L1, right? So L1 and C1, this is called C1, this and this together, they form a particular frequency, and the resonant frequency is 1 over square root of LC, right? We learned this in AC circuit theory, that when you have an inductor and a capacitor, they naturally resonate at 1 over square root of LC. And then the frequency in terms of hertz is 1 over 2 pi, 1 over square root of LC. And then this is C1, we're calling this. C1. Okay? So this frequency is going to be what? It's going to be in the radio range. 50 kilohertz to 50 kilohertz all the way to 1,000 kilohertz. So basically we're setting the value of the capacitance to whatever it needs to be. Together with the inductance, we're calling this L1, C1. Together, they're going to resonate and they're going to produce a frequency. So then you have the Tesla coil itself, which is going to be an air core double-tuned resonant transformer, which generates the high output voltage. So this one itself is also a transformer, air core double-tuned transformer, right? So then it steps it up again to the desired voltage that you have, right? Then it says, optionally, you could also put a capacitive electrode. This is the capacitive electrode right here. Capacitive electrode. So that is an optional feature. It says, it's in the form of a smooth metal sphere. It's kind of like a Van de Graaff generator. It's like a sphere, right? So then it says, or it's a torus. It's in the shape of a torus, like that, right? So it could be toroidal like this. A lot of the ones that I've seen on the online are in the shape of a torus. So that would be called the capacitive electrode. Then it says, its large surface area suppresses premature air breakdown. Premature air breakdown of the sparks. And then it says premature air breakdown and arc discharges, increasing the Q factor and the output voltage of the Tesla coil, right? So That would be the capacitive electrode. So then the features of it looks like this. We have your inductance L1 and L2, and C2 is the capacitance of the secondary windings. In other words, the windings themselves, these windings, the secondary windings of the L2 and the electrode E, right? So L2 together with C2 forms another resonant frequency, right? L2C2. So that L2C2 is the same as L1C1, right? L1C1. So the resonant frequency of this secondary should be equal to the resonant frequency of this primary, L1C1. So we can call this here omega 2 resonance. So W2 resonance equals W1, which is 1 over square root of L1C1. Okay? Okay, the next sentence says the specialized transformer used in the Tesla coil circuit called a resonant transformer, oscillation transformer, or radio frequency transformer functions differently from an ordinary transformer. Okay, actually this original transformer is a regular transformer. So we should put here, this one is a regular transformer. Okay, the second one is what's called a resonant transformer. So they're going to describe to you the difference of this resonant transformer from this regular transformer, right? While an ordinary transformer is designed to transfer energy efficiently from primary to secondary windings, so which is what this one is doing, from the primary to the secondary windings, it says the resonant transformer is also designed to temporarily store electrical energy, right? So this one is going to store electrical energy in its capacitor, right? So it has an inductor and a capacitor, okay? So then it says each winding has a capacitance across it and functions as an LC circuit, storing oscillating electrical energy analogous to a tuning fork. The primary coil L1, consisting of a relatively few turns of heavy copper wire, is connected to a capacitor C1 through the spark gap SG. The secondary coil L2, right, consists of many turns, hundreds to thousands. So it depends on how many you want to do. You can make this in your home. If you want to make thousands of them, you're going to create more energy, right? So hundreds to thousands of fine wire on a hollow cylindrical form inside the primary, right? So basically, this one goes actually inside of this. And you're going to see when I show you how this works. It's actually inside, and then there's an air core in the center. They don't put iron core. The secondary is not connected to an actual capacitor, but it also functions as an LC circuit. The inductance of L2 resonates with the stray capacitance C2, right? So L2, C2, they resonate together. So what is C2? It's a measure of the capacitance of the electrode and its own windings, right? So it says the C2 is a measure of the sum of the stray parasitic capacitance between the windings of the coil and the capacitance of the toroidal metal electrode, which is up here, right? Attached to the high voltage terminal. The primary and secondary circuits are tuned so they resonate at the same frequency. So W2 and W1 are the same. W2, W1, so 1 over square root of L2C2 is equal to 1 over square root of L1C1. This allows them to exchange energy, so the oscillating current alternates back and forth between the primary and the secondary coils. So even though they're not physically connected, this one and this one, but they still oscillate together because they have the same resonant frequency. It says, ordinary power transformers have an iron core to increase the magnetic coupling between the coils. And I'm showing you this in another demo where I showed you a regular transformer and there was an iron core that bound them. Here you don't want to put an iron core in the middle. Okay? It says, however, at high frequencies, an iron core causes energy losses due to eddy currents and hysteresis. Right? So you want to prevent energy losses. So it says, so it is not used in the Tesla coil. In the Tesla coil, you do not put an iron core. You just have an air core. So now let's actually show you the one that I have here. Okay, so you can see I have a light bulb here connected. I'm going to take the box out. Disconnect the light bulb. Show you the different parts of it. This is the original transformer, which is a regular transformer, right? And then you have these two capacitors together. These two capacitors are C1. So they would be basically this one in the circuit. And then this is the original transformer, right, which is this one here. This one is the spark gap. So if I connect this, right now I've got it connected. By changing this, I'm changing the distance. You see here? I'm changing the distance here. So basically I'm showing you this effect right here, the spark gap. And when the spark gap distance between the two plates, right, is the correct distance, then a spark is going to fly and form a circuit here. You see? So that means this transformer has already upped the voltage, and then I'm correcting the distance. I'm adjusting the distance between these two plates, and then a spark will fly and form a circuit. And this is my L1. See, it's the, you remember how I read, there aren't too many windings in the L1, right here. This is L1. So L1 and C1 form a resonant frequency. So when the spark fires, you see, I'm gonna change the distance now. I'm pulling it out. There's no spark. By adjusting the distance, the spark is flying. Then I'm storing charge in here, C1, and it's resonating with L1. But now this is L2. Okay, see, I put my fingers there, I got shocked. Okay, so this is L2. And you can already see that the L1 and C1 is resonating with L2 with its own C2, right? And so now the voltage is being stepped up from here to whatever that is, and that's voltage is about 50,000 volts. So now I put the box back on, then you can see this is the L1. Now I put the light bulb back on, adjust the spark gap again. And you can see the actual light bulb light up right here. Then you put your finger, see, you can see the spark. And then if I put this piece here, right, and if I bring the ground close to it, you can see the spark flying. You can see the light bulb. You can see the light bulb light up. And then when I put my finger on it, or hand, you can see as I'm doing, the spark will want to reach my hand, you see? One finger right here, 2 fingers, 3 fingers, the whole hand. I can make the spark follow me. But it's kind of safe because I'm doing it through the glass tube and it doesn't shock me. This is a different model of the Tesla coil. It has the sharp edge here, and it's got this thing which plays the same role as this. You see, by adjusting this, I'm creating a correct distance between the two plates, and then a spark is flying, and then all of that mechanism is happening inside of the casing, right? And then the sparks will fly from the end right here. So just turn this on, adjust the distance. Happening already inside of it. You see, then if I go to this one right here, see, very high voltage. I could use the Tesla coil to light up the gas tube here. You can see this is a helium tube. So when I bring it close to the helium tube, it lights up. It's kind of a yellowish color. And so there, I've excited the gas in the helium tube, and it lights up its natural color. The electrons make their jumps from their orbits, and you get the color of helium, and you can even do spectral analysis of that helium gas tube, right? Now let's take another tube. Okay, this one is mercury gas tube. Its natural color is kind of like blue-greenish, right? You see that? Put the Tesla coil near it. Really cool, huh? I don't want to bring it too close and get shocked, so I'm keeping it a bit of a distance. You can see here the spark flying and the gas lighting up. Really cool. Okay, this one is a neon gas tube. Neon is natural color. When it gets excited, is orange. We use this for a hotel or other kinds of stores for their signs, right? To bring attention to them. Let's see here what happens. Okay, my hand got a bit shocked when I got too close. So I'm going to keep it a bit of a distance. You can see the spark flying and the neon gas getting excited. So now you get a little bit more idea about the basic workings of the Tesla coil, what it was used for, what it is used for now, and then you can see some good demos. You could make this a good science project in your college or in your high school. Make your own Tesla coil. You can see the different models that are online. Watch some YouTube videos. Make your own Tesla coil, but always be careful because the voltages that it creates are very, very high. As you saw, I even got shocked when I was not careful. And you can do a lot of good demos with it, okay? Thank you very much.